All right. Hey, everybody. In this video, we are going to introduce the concept of a series. Our goals here are to first describe the concept of a series, to describe the relationship between a series and a sequence of partial sums. Remember, sequences are things that we looked at very recently. They're intimately connected to series. We're going to define what it means for a series to converge or diverge, and we are going to look at some specific examples. All right, so as a reminder, we recently discussed sequences, which were lists of numbers. Honestly, this should say infinite list of numbers, which had a first element, a second element, a third element, and so on. There was a starting point and there was a sense of order to a sequence, but there was no end, right? The list was infinite. A series is a similar idea, but instead of an infinite list, it can be thought of as an infinite sum and written as a list, as a summation of a list of numbers in a sequence. Right, so a summation, or a series in this case, would become a sub 1 plus a sub 2 plus a sub 3 plus ... And if we wanted to sort of highlight this concept, we would do that using this notation, and I would read this out loud as the sum from k equals 1 to infinity of a sub k, right? So this is a series, and we're bringing in our summation notation, but this time letting it sum up infinitely many elements of the sequence. Right, so right away, we have to try to understand what we mean when we talk about adding up infinitely many numbers. So how can we make sense of this? And this is actually a non-trivial question, right? So for example, I have the following three series as some basic examples. We have the sum as k goes from 1 to infinity of k. That's just 1 plus 2 plus 3 plus 4 plus ... And intuitively, this just seems to go on forever, right? This seems to, as we add on numbers, this summation will get bigger and bigger and bigger, and so that seems to go off to infinity. However, the second thing on our list, it's less clear what's happening, right? The sum as j goes from 1 to infinity of -1 to the j. Well, as j increases, right, -1 squared is +1, -1 cubed is -1, and so this will just go back and forth, +1, -1, +1, -1, +1, -1, infinitely. And so we have to ask the question, does it make sense to say that this series actually sums to something if we're just adding and subtracting 1 forever and ever? Finally, we have an example, sum as n goes from 1 to infinity of 1 over 2 to the n. That's going to be 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed, and so on. And so each of those terms seem to be getting smaller and smaller, and so there's some hope that this series will actually sum to something finite, right? But to understand what it sums to, or to understand even whether or not if it sums, we have to gain a better understanding of what it means for an infinite list of numbers to be added up and reach something finite. Now, to discuss this sort of fully, we have to introduce the idea of a partial sum. And so we have the following. Given a series written as a sub 1 plus a sub 2 plus a sub 3 plus ... I'm going to distinguish between something called the nth term and something called the nth partial sum of our sequence. So the nth term of our series, the nth term of our series is just going to represent a sub n, right? That's the nth element of our list. But the nth partial sum is really going to be the sum of the first n terms, right? So as an explicit example, if I were going to talk about the third term, well, the third term is just here. It's just that a sub 3. Well, the third partial sum would be this entire expression, a sub 1 plus a sub 2 plus a sub 3, right? So the partial sum is going to be the sum of the first several terms. And so what we can realize is that if I list out the first few partial sums, right, s sub 1 is just a1, s sub 2, well, that's just a1 plus a2, s sub 3, well, that's just going to be a1 plus a2 plus a3, and so on. I can begin to think about my infinite series as being intimately related to this sequence of partial sums that I have over here, right? And as I go further down the list of partial sums, as I get to s sub 4, s sub 5, dot, 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 uh, s sub 100, s sub a million, that is equivalent to taking more and more and more terms of my infinite series and adding them up. And so this gives us a way to examine series convergence, right? Or whether or not our infinite sum actually sums to something finite. If I take the sequence of partial sums, right? And it's an infinite sequence. And if that infinite sequence converges to a limit using our understanding of sequence convergence, then we would say that the infinite series converges to a number. And that's summarized in this gray box down here, right? A series converges to a number L if and only if its sequence of partial sums converges to L. And notationally, we would write it as it's displayed down there. Okay, so let's try to see this in action. So for example, if I tried to sum the sum as k goes from 1 to infinity of k, I could start listing the first few elements of my sequence of partial sums. So s sub 1 is just equal to 1. S sub 2, well, that's just 1 plus 2, so that's equal to 3, right? Oh, s sub 3, well, that's equal to 1 plus 2 plus 3, so that's just equal to 6. Right, and we see that our sequence of partial sums is clearly growing bigger. S sub 1 was equal to 1, S sub 2 is equal to 3, S sub 3 was equal to 6, S sub 4 would equal 10, S sub 5 would equal 15, and this is going to grow bigger and bigger and bigger. This is going to grow without bound. And so we can say then that the limit as n goes to infinity of this sequence of partial sums will actually equal infinity, right? The sequence of partial sums will just get bigger and bigger. And so therefore the infinite series will also get bigger and bigger. And so we can say that this series will actually equal infinity. At the same time, if we jump down to this lower example, right, we can see that s sub 1 is just equal to -1. S sub 2, well, that will equal -1 plus 1, so that will equal 0. S sub 3 will equal -1 plus 1 minus 1. S sub 4 will again equal 0. And we see right away that this sequence of partial sums is just going to alternate between -1 and 0. And so in fact, we get that the limit as n goes to infinity of this sequence of partial sums does not exist. Right? This is just alternating back and forth between +1 and -1. I'm sorry, between -1 and 0, -1 and 0, back and forth. So that does not exist, and therefore the infinite series does not exist, or I should say it does not converge to anything. We would say that this infinite series, use our language here, we would say that this infinite series diverges. Okay. All right, finally, let's get back to this more interesting example. So for this sequence, or for this series, I should say, what was the sequence of partial sums? Well, we've got s sub 1, it was just equal to 1/2. We've got s sub 2 was equal to 1/2 plus 1/4. That simplifies down to 3/4. We've got s sub 3 would equal 1/2 plus 1/4 plus 1/8, right? So that's 4/8 plus 2/8 plus 1/8. So that's going to be 7/8. Similarly, we will see that s sub 4 is equal to 15/16. That s sub 5 is equal to 31/32. And in general, s sub n is going to equal 2 to the n minus 1 over 2 to the n. Right? And so we can ask ourselves, well, what does this limit equal? Well, the limit as n goes to infinity of this sequence of partial sums is just going to be the limit as n goes to infinity of expressions of this form. And then that, of course, is just going to equal 1. And so we say that this infinite series actually converges to something finite. It converges to 1.